start recording. Okay, so welcome everyone to the edition of the Ringvorlesung. This is my fourth Ringvorlesung for the Max Planck Institute, and and especially for this lecture series. And I want to recall what we did last time and go a little bit more into detail about that. So maybe I have some here. So okay. Right. So last time, if you remember, we at the end, so after defining non-commutative geometry in the con aspect, we started doing this Moyal-Weil product. So it's in a sense a deformed product or a deformation of a product. Namely, you have a pointwise product and you replace that by an associative non-commutative product, okay? And this is what is known as the star product. There are many versions. Theta can depend on X in general, but the easiest and most straightforward one, and the one that is a lot used in physics, especially in applications to physics, is the one where theta is a skew-symmetric matrix, which is constant. And then, given a C infinity manifold, the algebra, as the functions over this C infinity manifold or a manifold, that let's say it's compact, and then you take the algebra of functions over that manifold, right? So you take all C infinity functions of that. And if M is non-compact, you can take, a sub algebra of that, which are the functions that are smooth and vanish at infinity. And then you can, define a new algebra, namely by the former algebra and the algebra with the star product. So this replaces the pointwise product, and it is given by this following exponential term here. So it's e to the I, the sum over k and j, theta kj, nabla k, nabla j, f of x, g of y, and then at the end of the day, sorry, here I missed that, you set x equal to y. So if theta is equal to 0, so let me correct that right now. Here you have x is equal to y, right? So if theta is equal to 0, this is just f of x times g of y at x equal to y. This is f of x times g of x. Okay, so this is also in a sense one of the ideas of this deformation quantization, that for theta equal to 0, the new product goes into the old commutative product. Right. Furthermore, there are properties of this star product. So the one that I just mentioned, this commutative one, is very important. Then there is also one that says it's associative, right? So if I take f star g, then star h, it's the same as f star and g star h. And furthermore, if you take the commutator of two functions with respect to this star product, this is equal to I theta, and the commutator of f and j, where here the Poisson bracket, and the Poisson bracket here for f and j is given by this skew-symmetric matrix, which is basically just a bunch of 0, 1, -1, and 0 in 2 dimensions, for example, and in n dimensions, 2 n dimensions, you can do it a little bit more general, and this is the Poisson bracket. So if you and the theta ij is basically given by this matrix times a constant theta, right? And now, of course, if I divide by theta and take the limits of theta goes to 0, what happens is I obtain this Poisson bracket. So the Poisson bracket is obtainable from the deformation quantization, or you can see it the other way around. The first order of deformation quantization, especially for theta equal to 0, theta being a constant, is obtainable by the Poisson bracket. Okay, so there is a sort of similarity there. And this similarity will sort of become more and more important. So maybe also something that I didn't mention here, but so if you insert for f and g coordinates x mu and x nu, right? What happens then is that in the star product, the commutator star product, or the star product commutator, so basically x nu minus x nu, x mu, well, instead of the product, you just replace it by a star product, you get 2 I theta mu nu. So you just need to use this formula do the expansion and then you will see it. I did it last time, and it is pretty easy to do as an exercise. And you see, the point is we have, so if we take this from a physical point of view series, right? So you have x mu minus x mu being equal to 2I theta mu nu, which means the coordinates are in a sense replaced by operators, and they do not commute anymore. So the measurement per coordinate is not as trivial as it is in classical mechanics. And there is an idea of quantumness, I call it, inside of that, because in a sense what you're saying is, instead of looking at the whole space-time, okay, so the space-time is the manifold we live in, for example, instead of looking at this, you know, as a just basically collection of points, what about we lose the point notion and look at it as a quantized, you know, version of that space-time, basically. And there are many reasons why, you know, one should look at something as well, to put it, you know, a little bit, well, I mean, to look at something as crazy as that, right? So one is the quantum mechanical principle that underlies the quantum mechanics is the uncertainty principle. And basically it tells you that the uncertainty of a coordinate times the uncertainty of the momentum of that coordinate is greater equal than h bar. H bar is some constant which is very small. That's why on day-to-day basis, we don't really notice the effects of quantum mechanics. However, if we would have sort of, you know, if h bar would be bigger, then we would notice things. And it's very weird. For example, there's the double slit experiment where basically particles have wave character and the other way around. There is also a particle wave duality. For example, two people go through a door, which is usually, I mean, if the door frame is big enough, nothing will happen, right? But let's say we have h bar is a little bit bigger. Then what can happen is what happens with waves, okay? There's a sort of fraction there, okay? And then we interfere with each other, okay? So there's an interference pattern, and then two people interfere with each other, and, you know, at the end, two different kind of people come out. So that could happen if h bar would be a little bit bigger. Now, there is an uncertainty principle which is equivalently important, which is the energy time uncertainty principle. It is more or less a relativistic generalization of that. And there is this quantum tunnel effect that can sort of be heuristically explained by this one. And if you take those two together and you take from general relativity the Schwarzschild radius, which is, you know, exactly the radius you have to shrink some object with mass m, such that it becomes a black hole. So in a sense, this mass is so big that it creates a singularity in space-time, and this singularity leads to a black hole formation, is given by 2mg divided by c squared, where g is just some constant, c is the speed of light, right? And now you can sort of do a heuristic explanation. Let delta r be 2mg divided by c squared, okay? So basically this. And instead of, and so here mc squared is the energy, so the most famous formula in the world, right? The energy is equal to mc squared. And then instead of mc squared, I put delta E and I divide here by C, and then I get, in a sense, delta R is greater equal than GH divided by C to the third delta X0. If I multiply delta X0 to the other side, I get a new uncertainty principle, okay? So it's an uncertainty principle which is a mixture of this and the Schwarzschild radius. And it turns out that, you know, localization of a space-time point has a certain limit. And since if I mean, I draw this picture here, so you want to localize the space-time point, right? And so you have to put some energy into the space-time point. And energy is usually done by photons. You want these photons to go there and be back reflected so we can see what happens, right? And basically what this tells you is that the uncertainty principle and the Schwarzschild radius can lead, you have to put so much energy in photonic energy into there that it creates a black hole. So there is a localization limit of, of space-time localizations. And thus, this is the first example. Then there are, this is, of course, you could say, well, this is a philosophical example, and you just took two theories that in principle don't have a lot to do with each other and are incompatible, and then you get some paradox, which is not a big idea. However, there are other examples. There are physical examples where the space coordinates do not commute. For example, you take the Landau effect. The Landau effect is basically you take some electron, okay, you neglect its spin, and you view it as a quantum mechanical particle moving in the presence of a constant magnetic field. So this can be described by a Hamiltonian that is basically 1 over 2m, where p is the momenta, minus Ea squared, where a is the gauge field. Now, a free quantum mechanical particle in the presence of a constant magnetic field can, okay, so you can solve the eigenvalue equation and you get eigenvalues, energy eigenvalues, which are quantized in a sense, which is also very interesting on it in itself. And B is here the strength of the magnetic field. E is just the electric charge. And sorry, is there any question? Okay. Right. Sorry. And basically in the lowest Landau level, what happens is that the coordinates that describe the movement of the electron do not commute anymore. And their non-commutativity is given by this magnetic field, or by the inverse of this magnetic field. So this is a figure that I took out of Isawa, the quantum Hall effect, which is also a very important effect in physics. As in mathematics, it is studied in the context of algebraic topology and K-theory and all that. And basically here it tells you that quantum mechanically, since the x and y coordinates do not commute, the electron position cannot be determined more accurately than the area 2 pi L square b. Okay, so there is a real non-commutative space going on there. So this is the second example where such spaces appear. Furthermore, I will give you a more, philosophical example in a sense. The relevant space in classical mechanics is the phase space, right? You have the phase space, which you have the coordinates and you have the momenta, and you define, there's a symplectic form to that, and then you define the Poisson bracket. Okay, I mean, I'm doing it very short just to give you an idea. So you have the Poisson bracket that is basically, the derivation of the coordinates and the derivation of the momenta. Now, in quantum mechanics, what happened is that you quantized the phase space. So you took this phase space and did a quantization. However, that is, you can now, since you know the star product, you can do the quantization via the star product. So you just use usual classical functions and replace the pointwise product by a star product. Or what you could also do is replace, the classical functions by operators, self-adjoint operators on a Hilbert space that satisfy certain, commutation relations that in turn give you this uncertainty principle. And the relevant space, in a sense, or space-time, and now here talking about space is a bit confusing, but so the relevant space in general relativity is the space-time manifold, and the space-time manifold is given by some points, on that manifold and so on. And so if we think to ourselves, okay, we want to save, if we want to do the same to gravity as we did to classical mechanics. So in classical mechanics, to go to quantum mechanics, we did this quantization procedure of the relevant space. And if we want to quantize gravity, the same has to be done here. We take the relevant space in general relativity, which is the space-time manifold, and quantize that. And the easiest quantization is one where you have x mu x nu equal to I theta mu nu. Okay, so this is sort of the main idea, if you want. Okay. Any questions so far, just to the main general motivation, sort of? Okay. Good. Now, just let me see a second. Now, so I mean, as I already explained to you, next we want to define a quantum field theory and a non-commutative spacetime. Okay, big words, and I will really explain in a little bit more detail what all of these words mean, but just a general picture. So quantum field theory is the theory of quantum fields that represent particles as excitations of fields that can be seen as, you know, infinite many harmonic oscillators. Okay, so take one harmonic oscillator and you do another and you couple them all, and then you have the field. Okay, and then an excitation of this field is what we see as a particle. So this is the viewpoint of quantum field theory. And basically you get quantum field theory, and this is, you know, very, it is so simplistic that it's almost wrong, but you can still learn something from it, that you take principles of quantum mechanics, principles of special relativity, meaning causality, and that that the speed of light, you know, has to be constant, and is constant, is the same, has the same value in all inertial systems, and you combine these two and you get the quantum field theory. Quantum field theory then combined, okay, and then with quantum field theory, you can do electromagnetism, you can do strong interaction, weak interaction, which are three of the four fundamental interactions which govern this universe. The fourth one being gravity. And now let's quantize. So, okay, the point is, why couldn't, so people went from here to here, and then, you know, we had three fundamental interactions. So U1, electromagnetism, SU2, which is weak interaction, and SU3, which is strong interaction. And they coupled them. So you get an electroweak theory by doing quantum field theory and coupling the gauge fields of U1 to SU2, and then you can do all of this. Then it's called quantum chromodynamics. Okay, so you can couple all three and describe basically all three fundamental interactions of this universe by using this framework of quantum field theory. And there's one missing, and that's gravity. And one tried to do it, but all, you know, the usual paths that worked for this, and worked for this did not work for gravity. So this is sort of the holy grail of theoretical physics, right? And this is why we do a lot of math. I mean, it's of course in one side it's the love sort of for math that we have, but also an interest for math, but also because we have a specific goal in mind, and that is, you know, the formulation of a complete theory of quantum gravity. Now, the ansatz in non-commutative geometry and deformation quantization is basically, well, non-commutative geometry, they had another approach, while, you know, the underlying philosophy was a bit alike. And in deformation quantization, you take these coordinates x nu as equal to I theta mu nu, so the commutator, where theta is the new constant. So I wrote here the constants, okay, that govern each theory. So in a sense, if h bar goes to 0, then you don't notice quantum mechanics. Well, these statements are very have to be taken with a grain of salt. So and the same holds for the speed of light. So the speed of light is sort of the main constant for special relativity, and the gravitational constant is the main constant for general relativity, right? And actually there is a lot of work done in that direction, that you can take classical mechanics and do a deformation quantization procedure using h bar as the deformation parameter, and then you obtain quantum mechanics. You can do the same classical mechanics, take classical mechanics and deform it in a certain way by using c, the speed of light, as deformation parameter, and then you get relativity. So in a parallel universe, if something like that exists at all, where people have knowledge about deformation quantization, they can actually come up with all these theories that are known to us by just taking the classical one and doing a deformation quantization. And now here we take the quantum field theory approach, and we infuse it with, you know, the space-time points being non-commutative, and therefore space-time itself being quantized. Now, how to do that? And in order to tell you and to explain to you sort of the really, I mean, the main points. Oh, sorry, I think I got. some notification. No. To describe to you the main points, I have to give you a crash course in quantum field theory. Okay, so it's a crash course in quantum field theory, and therefore, I mean, it will be simplistic, but I think I will cover, you know, I mean, at least for the free case, I mean, in a sense, a non-interacting case, I will cover the basics. So first, let us start with what we consider in special relativity, the space-time, which is the Minkowski space-time. Last time there was a question, I don't remember exactly who asked it. I think it was Sandra, but I'm not sure anymore, about what is a Lorentzian geometry, right? And the Minkowski spacetime is an example of such Lorentzian geometry. So you have the manifold M and the metric eta, and the metric eta is given in 4 dimensions, for example, as -1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And that is the convention I take. You can take the other convention, but these are conventions not that important. And there's actually wars for all of these conventions, well, whatever. So you have here the line element, that is minus c squared dt squared plus dx squared, and this is the sum over eta mu nu dx mu dx nu, okay? This is the line element. And now if you look at the Minkowski spacetime, basically we live here, right? I'm talking to you, and last week I was somewhere here, like talking to you and giving you all these, you know, rays, in a sense, that are transmitted via the internet. Now we're here, and tomorrow, if, you know, we will be here. So this is the time. And okay, of course, I cannot draw the 4-dimensional picture, but I can draw a 3-dimensional one. Here we have the hypersurface of the present, and everything in here is, in a sense, causally related. So you know, what happens here can influence what happens here, while what happens here cannot influence what's happened there, because, I mean, the time goes, you know, backwards. Now you take 2 random events, x mu and x mu plus dx mu, okay? And so in Euclidean geometry, which means in Riemannian geometry, which means in R3 or R2, you basically have a distance notion, which is, you know, you take the vectors x and y, and you take the difference, and then you take the absolute value of that, and then you have a distance. And that is strictly positive, and that's what makes you know, a Euclidean geometry and a Riemannian geometry the way it is. It has a positive definite metric, while here the positive definiteness is not there because of this minus over here, okay? And it has huge implications physically. First of all, I mean, 2 events are time-lag separated if ds squared is less than zero, sorry. If it is equal than 0, then it's light-like, which means it moves at the velocity of light, if I may oversimplify it. And d squared bigger than 0 is space-like. And 2 observers, so A prime and B prime, that are space-like separated cannot influence each other because they're causally separated, okay? And yes, so that is important to notice. So if they could, then the speed of light is not constant in all initial systems. That is the point. So there is and then you can see it as there is a sort of limitation to the speed with which events take place. For example, the sun is 8 light minutes away from us. That means that the light needs 8 minutes to come from the sun to us. Now, if the sun explodes right now, for the next 8 minutes, I will talk and record this talk and as if nothing happened. And you know, we're causally separated in a sense, because I don't know what happened there, and I cannot also not influence it instantaneously, but I need to wait the 8 minutes to get, you know, into sort of this cone again. And this is sort of the idea. I mean, maybe, right. So, so are there any questions so far? So this time I really didn't prepare too much, you know, slides, so in order to leave a little bit of time for discussion and so on. Okay. Sorry. Good. Now, a particle with 0 spin and mass m we call this particle, or the quantum field describing this particle, by phi, obeys the so-called Klein-Gordon equation. The Klein-Gordon equation is 1 over c squared d squared dt squared minus the Laplacian plus m squared phi equal to 0. Why this equation? Where does it come from? And for that, their answer is the correspondence principle. So in mechanics, the energy momentum relation is E equal to 1 over 2m p squared plus v. And the correspondence principle basically tells you, in order to get this quantum effect, take the energy and replace it by time derivative, take the momentum and replace it by the derivative with respect to x, and let any operator x be understood as the multiplication operator with x. And then you go from classical mechanics to quantum mechanics by obtaining the Schrödinger equation by this so-called correspondence principle. And so it all relied on this energy momentum relation, right? Oh, now we have this, I don't know why. All right. So this meeting will end in 10 minutes, then we will have to restart this thing again. I'm sorry for this. So, so the relativistic dispersion relation, or energy and momentum relation, is, you know, the formula. If P is equal to 0, you have E to the E is equal to mc squared. So this is basically just a relation between the mass of the particle, the momentum of the particle, and the energy. Now, disregarding the potential. And here I do the correspondence principle. I set these constants equal to 1 because, I mean, they're physical constants, and in a sense, they're not that important. It's just like having a pi somewhere, right? And then I obtain, so E, I put this in, E dt squared is dt squared minus, and P is minus the Laplacian, and m squared is just m squared. And I put this together, and this is the Klein-Gordon equation. And okay, just to give you sort of a notion, there is a generalization to curved Lorentzian manifold. So a curved Lorentzian manifold is one where it's not just minus ones over there, but the metric has some functions depending on x, right? And in that case, the Klein-Gordon equation looks a little bit different. So it has also the possible, so psi is just some parameter, r is the curvature. And then you can boil, so for a metric of the form minus n squared dt squared plus hij dxi dxj, you can boil it to this. Okay. So, right. Now for a metric g minus n squared plus hij dxi dxj, you get this form of the Klein-Gordon equation, where omega squared is basically a Laplace-Beltrami operator plus some weird potential, right? And in general, you can, so, right, you can show that this manifold, so if this manifold is globally hyperbolic, for those of you who knows what globally hyperbolic means, it means that the manifold can be sort of seen as a product, direct product of R and sigma, or sigma is a Cauchy surface. A Cauchy surface means that a subset sigma of M is called a Cauchy surface if every time-like curve in MG intersects sigma exactly once. And you know what I was able to prove with Oekel in 2018 is that if the Riemannian manifold n to the minus sigma n to the minus 2h is a complete Riemannian manifold, then omega square is an essential self-adjoint operator on C0 infinity. And complete Riemannian manifold, or you know, you can say complete Riemannian manifold or geodesically complete, means that every geodesic is isometric to the real line. Basically, it means you have geodesics and they are defined for all of R. For example, you take the case of R and delta, the metric, then the geodesic equation is just d squared x to t squared, and the solution are just, you know, the straight lines. And this is in a sense defined for all t's. Okay, so if you would have here 1 over t, then you're in trouble. That is sort of the thing to remember here. Yeah, sorry. So right. Now back to the flat case. The solutions of the one particle Klein-Gordon equation can be written as a sum of normal modes. So you have a particle annihilation operator and a particle creation operator, they call it. And here you have omega, where this is the frequency of the normal mode. So you have a mode splitting, the one that you usually know from Fourier analysis and so on. And each normal mode corresponds to a single p, can be understood as a classical harmonic oscillator with frequency omega p, where, okay, the energy can be plus and minus, and what we call the second quantization sort of takes care of that, but that is maybe not that important. What is important here is the following. In quantum mechanics, you replace points by operators. Now, in quantum field theory, you deal with fields. And in order to solve for these fields or quantize these fields, you replace them by operator value distributions, because the field on itself is a distribution. And now you put on this field, you know, an operator, which makes it an operator value distribution. So now we're talking about operators here, okay? And this going from here to here is a sort of, you know, tricky, it's a tricky path. It's not, you know, that clear sort of. And basically you have, you know, e to the omega p minus e omega pt plus epx. Oh, sorry, I should, wrong here. So this is plus, sorry, this is minus e omega p t, where omega p is just the energy of this normal mode. AP plus AP dagger, and these fulfill certain commutation relations, which you call the canonical commutation relations. Now, what is, as I told you, I mean, the point is quantum field theory sees the world as, you know, it's, you know, everywhere is sort of this quantum field, and they're all harmonic oscillators basically. And, you know, if you excite one harmonic oscillator, then it gives you sort of some frequency, and this excitation is what we call the particle. And the vacuum state of the lowest energy is defined by AP on 0 is equal to 0. Okay, this sort of this right, this annihilation operator applied on this vector 0 gives you 0. And that's why they call it annihilation operator and creation. Okay. Now, there's this famous saying by Nelson, which says the first quantization is a mystery, but the second quantization is a functor. So for you who are familiar with functor theory, this might be surprising and funny, because, I mean, that we had to do the first quantization, which it means replace the classical mechanical phase space variables by operators. That is a mystery. No one knows why this, there's no real explanation for that, except for it, this is a solution to a problem. Now, the second quantization is a little bit different. The second quantization, you take one particle Hilbert space, and then you tensor it, and then you take the sum over all that. And that is what is called the Fock space. Okay, so this is basically what I meant by replacing this operator valued, this distribution by operator value distributions. Is I quantize it for a one particle space, and then I do it for n particle subspaces. Now, what is important is now that this, you know, this distribution, operator value distribution, needs to be smeared out, as all distributions have to be. And you use the function f equal to c0 infinity of m for that. So a function that is smooth and has a compact support on this manifold. And this is what we call with smearing out. And then, you know, this field satisfies a few important properties. It's complex linear. The adjoint of it, the adjoint of this field is phi of f bar, so the complex conjugation, which means if f is a real function, we can prove that this operator is a self-adjoint operator. Furthermore, it fulfills the Klein-Gordon equation. So this P here is the Klein-Gordon operator. And what is maybe also, I mean, the most important is that if I do a measurement in F prime, so now this is so remember this cone. If I do a measurement here, and if I do a measurement here, they are not allowed to interact or interfere with each other, basically. That means if I measure here, then here, it's the same as measuring here and then here. So, and that corresponds to, in this language, the field operators commute. Okay, if the support of this function is, you know, in one part of this cone, and the support of the other function is in this, you know, if the supports of the functions f and f prime are space-like separated, is what is said there. Okay, now I gave you a very quick crash course in quantum field theory. Quantum field theory, Minkowski spacetime. For free Minkowski spacetime, it's this quantum field that obeys certain equation called the Klein-Gordon equation. One obtains it by this correspondence principle and taking the relativistic energy momentum relation. And then one solves for it and does something which is called the second quantization, which is basically I solve for the one particle space, I replace the distribution by an operator, and then I define it for n particle spaces. And now what I want to do is define a quantum field on a non-commutative, on a constant non-commutative space-time, and how that